This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Good afternoon, everybody. Welcome back. I hope you guys enjoyed your mid-semester break. Congratulations to those who actually managed to find the lecture theater. It's a bit hidden. And so today we're going to continue talking about indexing. So it was the last thing we did on our previous lecture. But before we do, let's just make a quick, very quick recap. So instead of actually pointing here, this is a bit of awkward position, I'm just going to use this pointer. Is that okay? Yeah, everybody can see that? So basically the context was the following. We had a lot of information. And the question was, how do we find the information we want? So we live in a post-genomic era. We're dealing with terabytes, petabytes of data, and we need strategies to find this information. And it has to do with selecting the appropriate data structure. So if we have the analogy of books in a library, which library we look for, which book, which chapter, which page, we want to be able to robustly access information as quickly as we can. And that's done with the concept of indexing. And basically, indexing is a mechanism for speed up access to a given desired data. And on an indexing, we will have a search key, which is an attribute, a set of attributes that we use to look up a record in a file, and the actual index file that actually records our data. So if we look at a summary in the book, we'll be looking for sequences or sentences that will be indexed to specific pages where they occur. And there are different indexing approaches. And we also discussed about the importance of indexing in the genomics studies context, and it's extremely important for the BLAST algorithm. So actually it's one of the main reasons for the speed up BLAST achieves, which is basically the index phase, where it index small sequences, both from your query sequence and your database. In that way, it can look it up where it appears in your reference genome, for instance. And basically, the motivation for BLAST there was making the alignment of millions of strings to a reference genome feasible. And what we want for index also is as small as a memory footprint as possible. And we started discussing about k-mer indexing. And the first idea was actually have the k-mer as a key, and where it appears the index. So we could, from a given read, generate a k-mer index like this. And if we make this a vector in a alphabetic order, we could then retrieve k-mer appearance using binary search, which takes logarithmic time to run, because it's basically will find then different bisections, and by dividing the data every time into bisections, we have a very quick and efficient way to select the data. And the other data structure we discussed was hash tables. So can we go faster than a logarithmic time? And a hash, or a dictionary, is basically a data structure composed of two different parts: an array or a table, where the data is actually stored, and a mapping function or hash function that is responsible to map a given key to a specific index in that array, which is also called a hash bucket. And for that, we have a key value pair. And there are a few important things when we need to select hash functions, for instance. What makes a good hash function? So it needs to be fast to compute. If we have a hash function that is slow, we lose all the gain advantages for the quick lookup time. We want to map to finite size output values. We also want something that is deterministic, so we can access our data reliably and retrieve our data. And we also want to produce good distribution of values over the table to avoid as many collisions as possible, because collisions deteriorate performance. And if we do have collisions, and that happens, that's very normal, we need to solve them. And one way to resolve collisions is using linear probing. For instance, if we have an array, if that position in the array is already occupied, we just use the next one. That has the downside of a table that is clustered, so we don't have a proper distribution. An alternative will be chaining, so using, instead of an array, a linked list. So each index in our bucket, instead of an array element, is a list, and if we encounter a position, we just add another element. Very simple and easy. The downside, of course, is that if we don't have a good hash function, searching times will deteriorate. And if we do have a good hash function, we can assume collisions are fairly rare. So we can assume we'll always get lookup time in constant O1 time. So as a summary, hash tables would then, if we want to index k-mers for a genome of length m, it will take OM time to build the table. But once the index is built, we don't have to look at it anymore. We can just use it. And it's constant time to look it up. And also uses OM space requirement. And the limitation is, well, if we want to allow mismatches, instead of just looking for a exact match, what if we want to allow mismatches? And that's quite important when we are dealing with sequences. And again, good hash function will be well distributed indexes, will be quick and deterministics. But something to remember is that hash keys are inherently unordered, no ordered in the way they are stored in memory, differently from an array. So index I and I plus 1, they're adjacent in memory for an array, not necessarily for a hash table. Okay? And today we're going to discuss a few different other approaches to indexing, and most of them have to do with something called suffix-based index. What's a suffix and what's a prefix? Is that clear? Everybody knows what a suffix of a sequence is and what a prefix is. Okay. So, in the first data structure that is quite important to indexing words and strings are actually tries. So a trie is a type of tree data structure that represents collections of strings as keys and their values. So basically, the edges of a trie store the entire alphabet. One edge stores one character. And strings and words that can then be retrieved from the trie, right, traversing down branches from the root to a given leaf, okay? And we want the smallest tree such that each edge is labeled with a given character C from our alphabet. Let's say if we have the English alphabet, we'll have 26 different character possibilities. And for a given node, at most one child edge has label C for any C belonging to our alphabet. Okay, so it's a very simple concept. And tries are very helpful to implement a set or a map when the keys we're using are strings. For instance, if the keys are reads or k-mers. So every trie has then an empty root. We always start with a node that is empty, doesn't have any information on there, which is our root, and it will be linked to other nodes. And each edge will then represent a possible alphabetic value. If we're using English, that will be 26 different possible children at most per node. Okay? And let's say we want to insert keys or values. So let's say we want to insert the following words: instant, internal, and internet, with the following values, 1, 2, and 3 respectively. What we would do is basically starting from the root, we will then check for each character of the string, let's say instance is starting from I, check if the edge for that character starting from the root exists. If not, if it does, we continue traversing down. Otherwise, we create a node and label edge. And when we finish up, we create another terminal node. Oopsie. This is very annoying. Create a terminal node with the value for the key. So for instance, INSTANT. Once we finish going through all the characters, we add one more node, which is a terminal node, with the actual value we want to store for that key. And how do we search on tries? So it's a very intuitive, very simple issue. So how do we check whether the word infer is present in our given trie? We know it's not there because it's just composed by instant, internal, and internet. So the basic algorithm is starting from the root as well. For each character in our search string, we'll check if the edge of that character C exists. If it does, we traverse down, we keep going. Otherwise, the search has failed. For instance, with infer, we will have a first match with the character I, then another match with the character N, but we don't have the next one, which is an F, so our search has failed. If it continues, and if we reach a terminal node, a node with a value, then we have a match. That's how we search on a try. Let's say we try a different word, interesting. It would be the same process, so character by character, assessing whether we have the edge or not. Eventually, in this case, we don't have an E here after the R, and then the search failed. And let's say we want to check whether the word Insta is in our try. We'll do the same. In this case, Insta is a substring in the tree, but not a word inserted into it. So we matched all edges, but there's no value associated with the node we finish on. So this is not a match. Therefore, Insta is not a key for a try. Okay? What about the word instance? If we try instance, then we reach a node with a value. Therefore, instance is a key with an associated value of 1 in our try. Okay? And so checking the presence of a key for a string, let's call it P, and let's consider it has n characters. We'll traverse at most n edges, 1 edge per character. So how to represent edges between a node and its children? And that's very important because we need to be able to quickly look it up. And, well, let's say we can have up to 26 children, and we need a way to index this. So each of the children here, when we say, is there edge n? I need to be able to quickly look it up. One idea to do that is using a hash table. We can do that in O1. Alternatively, we can use our children as a sorted array, right? And again, with a sorted array, we can use binary search and look it up in logarithmic time with binary search. And let's assume then that we use a table hash to do that. What's the time complexity for querying P, a given word of n characters? That's, of course, linear, O(n). And for instance, tries can be used to represent a K-mer index fairly easily. And what we could map with the values are actually the offsets where the K-mers occur. Okay, so with the terminal values, we would have the indexes where each of the K-mers occur. The K-mers would be represented by a path from root to the leaf. Okay, so we could use a try instead of a hash table to map K-mers with a lookup time of OK, which doesn't seem too good considering a lookup time of a hash table is O1, but usually the value K is small and it never changes in the context of a given try. So we could even consider that the lookup time in that case for K-mers is constant as well. So it's a very efficient way to index K-mers. And one advantage is it won't have collisions, so we don't need the hash functions. If our number of K-mers is way too big, hash functions will eventually generate collisions, so this could be even more appropriate and quicker. So what's the time complexity to create a try? Is O(m) times n, where m is the longest word and n is the number of words we have. But once we create the index, we don't need to do it again, so we have it ready to use. And there are different other applications to try. So we use tries on a daily basis without knowing it. So tries are usually used in combination with other structures or in context of an algorithm. Can anyone tell me an example of an algorithm, a daily thing we do that could be used with tries? Probably never noticed this, but autocompletion. You can implement autocompletion using tries. And that's how Google does. So when you start typing S and then P and then A, what it's doing actually is ranking the most relevant terms and showing a traverse down that path in the try. Okay? So it's a very common thing to use, very useful, and it generates a very efficient way to access information. If you consider on a Google search, you have billions and billions of potential terms, and you can actually retrieve them extremely quickly. Okay? Of course, there are alternatives to tries. They are not the only way to encode sets of maps over strings using a tree. And a different approach would then be using suffixes instead of the whole word. Okay? So we might be interested in just indexing suffixes. And these actually yield surprisingly economical and practical data structures. And for that, we have two data structures that we're going to discuss. The first one is suffix tries, and the second one, suffix trees. And we'll see what's the difference and the compromise between the two of them. So suffix tries. So let's build a trie containing all suffixes of a given text T. Let's say the text T is a read, and we have this read here. And we have all m possible tries. Okay? This will then generate a matrix with m times n plus 1 divided by 2 characters. Quite a few characters. But before we do that, what we're going to do for suffix tries is add a terminal character, $ to the end of T. And that's a very important step. Okay? So, and $ is a character that does not appear elsewhere in our word. Okay? In our text. And then we define it to be to precede other characters, lexicographically, okay? This is very important as well. So the first character in the alphabet now is the $. So, and then we have A, C, G, T, and so on and so forth. In this case, that's all our alphabet, okay? So two important things. We need to append it to the end of our text, and we define it as preceding other characters, okay? And by using this $ character, we enforce a family rule. For instance, the AS word will come always after ASH in the dictionary, okay? And this is important also to guarantee that no suffix is a prefix of any other suffix, okay? Because AS terminal is different from these ASH here, okay? Otherwise, this would be a prefix of this, and I want these suffixes to be different, and no suffix can have a prefix. It can be a prefix of other suffix. It's very complicated to say. Is that clear? Yeah? We'll see that how this is important and also this in a few seconds. So conceptually, what we need to do is every suffix is indexed with its original position. For instance, the whole string will be position 0, the next one will be position 1, and so on and so forth, until we covered all of it, including the last character. So the last character, the $ character alone, will also be indexed. So let's try to create a suffix tree for a very simple word, ABA, and then our terminator character. So first thing we're going to do, creating all suffix and indexing them. So ABA $ is 0. Then we have our next suffix, and the final suffix, which is empty just with the terminal one. And what we do is we're going to create a suffix tree, and we'll insert all these 4 in the tree. So if you remember the algorithm, basically starting from the root, we'll check if there is an edge for each of the characters of the word. The first one is A, for instance, and then we create it because it doesn't exist, then B, then A, and we always finish with the terminal character there. And we proceed doing the same thing for the other suffixes. And then we end up with this suffix tree. Yeah?
Isn't ABA the actual word and not a suffix?
By definition, the actual word is also a suffix.
Okay.
And the actual word is also a prefix. Let's consider that the prefix, the suffix in this case, needs to have at least 1 character, and you can have up to all characters. Sounds okay? But it's just a definition. And then let's try to create a suffix tree for a smaller, slightly longer tree, a longer word, and we'll have something like this. And each path from root to leaf will represent then a suffix. So if we go from here, BA and terminal, that's BA, that's 1 suffix that is right here for this word. And each suffix in the tree is represented by some path from root to leaf. So these are 2 properties that are quite important for suffix trees. However, would this be the case if we hadn't added the terminal, would we have this exact same tree? Would we have each suffix being represented in the tree without this, considering the rules we set to how to insert things in the tree? Not really, right? Why not? Because we will have something like this. So since there are repetitions here, and this is even a palindrome if you look right here, we would have suffixes. They are prefixes for other ones if we don't have the terminal. We would end up with just 1, 2, and 3 different suffixes. And the fact of the matter, we have 1, 2, 3, 4, 5, 6, and 7. Okay? So adding the terminator character is quite important in that sense. Okay? So how do we check whether a string S is a substring in our text, considering suffix trees? So we can consider that every substring is a prefix of some suffix of our text. And every suffix is on our tree. Okay? So the only thing we need to find is a suffix, and then traverse the tree and check whether it's there. So also the strings are spelled out along a path from the root. So we just start from the root. For each character of my query sequence S, we follow the corresponding edges. If we fall off the tree, or actually we fall off the trie, it means there is no outgoing edge for the next character, which means S is not a substring of T. If we exhaust S without falling off, then S is a substring of T. So if we consider the word BAA, we start from the root, we follow the edges, BAA, okay? And then BAA is a substring of T. What about the substring BAABB? So BAAB, and I just fell off the tree. So there is so BAABB is not a substring of T. BAA, on the other hand, is. And this is basically the same procedure as for substring we can perform to asking the question whether a string is a suffix, which is different from a substring. So basically what we want for a suffix is finishing up on a terminal node. For instance, BAA is not a suffix because even though it's a substring, it's in the tree, it doesn't finish in a terminal node. Okay? If we consider ABA, on the other hand, ABA, then we can finish with the terminal character. Therefore, ABA is a suffix on the tree. We can also ask the question fairly simply, how do we count the number of times a given string occurs as a substring of T? We basically follow the path labeled by our query sequence. If we fall off, basically the answer is 0. I have no occurrences of that string. If we end up at a node n, let's say we end up here at this node, basically the answer equals the number of leaves in the subtree that is rooted on n, in this case 1 and 2. Okay? Basically it's the number of matches we have for that substring. And then we can, from n, count the number of leaves we have, for instance, using deep first traversal. How can you traverse a tree in deep first search? There are 3 different ways, right? How do you do that? Do you know how to do that? What are the 3 different ways to traverse a tree in deep first search? It's likely different from graphs. In order, pre-order, post-order. What's the difference between them? The order in which you visit the node. So pre-order, you visit first, you go left, you go right. In order, you go left, you visit, you go right. Post-order, you go left, you go right, and then you visit. And that has the effect when you're doing for instance, you're implementing it recursively. Only when you can't no longer go left on in order, then you visit the node. Okay? But basically here, for counting the number of strings we have, we just need to do a type of deep first search and count how many leaves we have. Okay? And using tries, how do we answer the question, how do we find the longest repeated substring in T? basically all we need to do is find the deepest node with more than one child. Okay? Deepest node meaning is the longest one. More than one child meaning it's repeated. Okay? It appears more than once. And of course, using tries is a very flexible data structure. You can ask all sorts of questions. For instance, you can implement using tries, longest common substring searches. You can query allowing small number of mismatches as well. So while traversing, you can keep a counter, for instance, and say, well, even if it's not the edge I want, I'll traverse anyway and keep going. So it's a very flexible way to do it. And how does the suffix try grow with the size of our text? Let's call the size of our text m. Is there a class of strings where the number of suffix try nodes grows linearly with m? Number of nodes in a tree. That's basically the example here. So if we have a string that is predominantly made of repeated characters, what's going to happen is we'll have, let's say, a lot of A's in a row. And for instance, in this case, our string is only composed by A's. The number of nodes is 2m plus 2, which is basically one root, m nodes with an A edge, the parent, m plus 1 nodes with our terminal edge. And is there a class of strings where we have the worst case scenario? For instance, the number of nodes is growing quadratically. Can you imagine a class of strings that does that? Basically, I need to mix up A's and B's. But the way I do it is basically separating them into bits. So let's say we have a text of size m, and we have n A's followed by n B's, where 2n equals m, and that would generate a quadratic number of nodes. So one root, 2 plus 1 terminal nodes, which are not shown here, n nodes along the B chain, n nodes along the A chain, and n chains of nb nodes hanging off A chain, which gives a total of n squared. And actually, this is the best and worst case scenario for suffix trees. But empirically, so a lot of people have actually implemented suffix trees for indexing genomes. For instance, this is a real graph showing the number of suffix try nodes for the first 500 prefixes of lambda phage virus genome. The black curve is the actual value. You can barely see, but I promise there is a red one on top, which is the worst case scenario, and it's a blue case scenario right down here. So the actual growth for suffix tries in terms of the number of nodes is much closer to the worst case scenario than the average or even than the best one. So how do we make tries smaller? One way to do it is then coalesces non-branching paths into a single edge. Well, instead of just representing this as A, B, A, and then the nth terminal, we just call it ABA. So there's no point in representing this if this is a non-branching path. There are no branches coming out of here, so I can just merge things. So I can just zip them and coalesce non-branching patches and represent, instead of having nodes for everything, just putting the string here. Okay? And this, of course, will reduce the number of nodes and number of edges in our tree. And will guarantee that non-leaf nodes have more than one child every time. Okay? And then we use better the space as well. So let's consider then our text has m characters, how many leaves we would have. So in this case, we would have m leaves. How many non-leaf nodes we have? We'll have less than m minus 1 if we do that, for a total nodes of less than 2 m minus 1, which is linear, which is good. And this is actually a slightly different data structure called a suffix tree. It's not a try. A try, by definition, each edge is represented by one single character. And in this case, in a suffix tree, we'll have a set of characters. Okay? So it's a more compact representation. However, the total length of the edge labels will still grow quadratically. We'll have less nodes, but we'll still have to store all of these characters here, which still grow quadratically. Okay? So idea 2 will be, let's modify the suffix tree slightly. So to store, instead of the whole thing, we'll just store the offsets and the length pairs. Okay, so instead of saying ABA terminal, I say ABA actually appears on position 3 and has a length of 4. So if we have this following text here, ABA, ABA, if we want to represent this bit here, which is BA, instead of having the actual characters there, I can just say the index where it appears, index 1, second character, and the length, 2 characters. That means I can represent everything now with just integers, which brings down spaced complexity to linear. Okay, so worst case scenario, we'll have a something that is proportional to the size of our initial text. In comparison with the suffix trie, it's a huge gain. Okay, and in suffix trees, our leaves will hold offsets. Okay, and basically what we could have if we traverse the tree and we reach the bottom, what we would have in the leaf is actually where this suffix appears. Okay, so if we traverse this here, this is the 6th and last suffix, which is A. Okay, and the labels will have 2 notions. The first one is node depth, which is basically the number of edges from root to the nodes. In this case, this here will have a depth of 2 because we have 1 and 2 edges from the root to it. And in terms of label depth, will actually be the total length of the edge labels from the root to the nodes. And in this case, I have a label with 2 characters, a label with 4 characters. In total, we'll have a label depth of 6. Okay? And in terms of methods for building a suffix tree, all we could do is, let's build a suffix trie, and then coalesce non-branching paths, and relabel the edges as we do. And this will take quadratic time and quadratic space. The second method, however, it's building a single edge tree representing first the longest suffix, then augmenting it to the second longest, and so on and so forth. Okay? And this brings the space-time to OM. But usually the simplest one, the one that we could do manually, will be building the suffix tree and merging non-branching paths until we can't anymore. But there's also a canonical method that we're not going to discuss, that Uconen's algorithm proposed in the late 90s, that actually manages to do it in OM time and OM space. So it's possible. So if you're going to use an actual implemented suffix tree, it's likely that you're going to use this one, that is linear both in time and space. This was proposed in 95. So, but yeah, in terms of the number of nodes, if you compare a suffix trie and a suffix tree for the same input, while a suffix trie will generate, for this case here, over 100,000 nodes, suffix tree will have less than 1,000. So it's considerably lighter footprint in terms of memory. So how do we check whether string S is... Oh, great. Touch to activate. Touching. Okay. Come on. It's warming up. There you go. Thank you. Question with the suffix tree. Same thing with the suffix trie. If you want to match and ask the question whether string S is a substring of T, what we need to do is basically the same procedure as we did for tries, but we have to deal with coalesced edges. So if we ask the question whether BAA is a substring, we'll traverse the tree in the same way, BA, and then we go to this edge. So A is only a prefix of this edge label, so therefore it is a substring. Same thing if we want to check whether a given string is a suffix. We'll also have to deal with coalesced edges, but we'll just make sure that we finish on a terminal node. Okay, and in this case, AB is a substring, but not a suffix because it doesn't finish on a terminal node. Okay? And how do we count the number of times a given string occurs as a substring of T? Same procedure again as a suffix tree, and we'll have then the number of leaves as the response. And we can also count or find all the matches of a given substring to T. Let's consider then K be the number of matches, and let's consider that we have as a query AB, and we have ABA as our text. The first step to then match, either count or find all the matches, we'll then walk down the AB path. That takes ON, considering the length of our query. If we fall off, there are no matches. If we visit all leaves below, that's OK in terms of the complexity, and we report each leaf subset as a match of set. And this will take ON plus K, so linear time. So in summary, in terms of tie complexity bounds, if we have then our text of size M and our query of size N and K occurrences from S as a substring of T, we'll consider that a suffix tree is efficient in terms of space. So we have OM space. And linear space is desirable. However, there is a constant factor that we're not seeing, which is implementing a tree is not that simple. You need to keep track of a lot of pointers. So there's a constant factor regarding suffix trees that on itself might be limiting. That's the difference between saying I have two quadratic algorithms, and one scales with 100 times n squared, the other one is 0.5 n squared, so there's still 200 times difference between them. And that's basically the difference between these data structures. And this constant factor is basically how many bytes it requires to actually use per character. And it varies depending on implementation, but for instance, MUMMR, which is a famous algorithm for whole genome alignment, the constant factor for indexing it is actually 16 bytes per base pair. Okay, that's quite a lot. If you consider a small-ish genome, 250 million bases, that's 4 gigabytes in memory. If you consider the human genome, that will require a suffix tree of over 45 gigabytes, probably considerably more, depending on implementation. So even though it's linear in space, it depends on actually how bad this constant factor is. And an alternative to try to have a lighter memory footprint are actually suffix arrays. So how do we spend actually less memory to build this suffix? And a suffix array of T is basically an array of integers from 0 to M, not including M. And we're basically specifying lexicographic order of the suffixes of T. Okay? So in this case, we only need to store the sorted indices. And we do this as follows. Let's say we have our text T, ABA, and we want to create a suffix array for it. First thing we do, we're going to create the indexes for the suffixes. We have 7 suffixes. Again, in the same way we did the suffix tree, we including the terminal character to it, and we have the suffixes indexed from 0 to 6. However, the way we're going to insert it in an array is in a lexicographic order. So the first one, by definition, is always the empty character, because we define that this precedes every other character in an alphabet. So this is the first one we insert, and we insert it with the actual index where it appears. And we keep inserting them sorted lexicographically. So the next one will be A, and then AABA, and so on and so forth. Okay? So this will be then the suffix array for our word. And the effect that we'll have in terms of the space requirement is that we'll still need OM space, like a suffix tree, but the constant factor is considerably better. Okay? Why? For instance, if you consider the size of the human genome, we have 3 billion base pairs. And let's say we have an index of 32 bits. So with 32 bits, how many integers can we represent? How many integers can we represent with 32 bits? Yeah? With 32 bits, we can actually represent 2 to 32. It's quite a lot. So it's equivalent to 10 to the 10th, right? And that's more than what we need to represent the human genome. So we can actually use 32 bits, which are 4 bytes per base pair, times 3 billion base pairs. That gives us an index of 12 gigabytes, which is considerably smaller than a suffix tree, which is at least 45 gigabytes. So we saved pretty much 3/4 of the space there. So how do we query a suffix array? So the question is a given string a substring of t? And basically, for S to be a substring, it needs to be a prefix of at least one of the suffixes. And we can use the fact that this is actually lexicographically sorted to use binary search, right? So since this is sorted, we can access the question whether S is a substring of t in logarithmic time, okay? And how do we build this suffix array? There are different ways to build it. One way to do it is actually building a suffix tree and then traversing the suffix tree in alphabetic order and then inserting them in order in the array. But of course, if you reach then a leaf, you append it to the suffix array. But of course, the most interesting and simple idea would be just you put everything on an array and you sort it. Basically, you can sort anything on n log n using an algorithm such as quicksort. But there have been more recent algorithms that we're not going to cover that also are capable, that demonstrated that they are capable of building the index for a suffix array on OM as well. There are at least a couple of them. And that brings to the last type of indexing. So far, we've been reducing our memory footprints, and our goal is to index the human genome with a suffix tree will span over 45 gigs, with a suffix array over 12. Can we do better? And with the Burrows-Wheeler transform, we can. So it's a very interesting, a bit complicated, but very interesting transform. It's a reversible permutation of characters over a string used originally for compression. So the BZ2 algorithm actually uses the BWT transform. And it works as follows. So we start with our T, which is our text. And we'll do all possible rotations of this. And I'll show in a bit what a rotation means. And that will lead us with something like this, which is an array or a matrix of all possible rotations. And basically, our Burrows-Wheeler's transform is the last column. So basically, all we need to do is first make a list of all rotations. So this is our original text. Our rotation would be removing the first character, appending it to the last, then removing the next, appending it to the last, and then we have one rotation, the next one, and so on and so forth. Okay? And what we're going to do with all of these rotations is basically sort them alphabetically. Again, considering the terminal character, okay? And we'll end up with the Burrows-Wheeler matrix, which is something like this, okay? So it's alphabetically sorted. And basically, our Burrows-Wheeler transform is taking the last column, simply the last column, okay? And this is going to tell us a few interesting things. So the Burrows-Wheeler transform orders T's characters, the characters of our text, according to alphabetic order, based on the right context. And the right context looks like this. So the right context of a position in T consists of everything that comes after it with a wraparound. So the right context of the first character is everything that comes after it. The right context of the fourth one is everything that comes after it plus the remaining. So starting again. So the right context of this character A is BA, terminal character ABA. Is that clear? So then with the BWT transform, what we end up is basically one column and a right context. Okay? And I mentioned this is reversible. So using something called LF mapping, we can basically return from this, the transform, to the original text. And it works as follows. So let's give each of the characters of our text a rank T. Okay? And this rank is basically the number, is an index with the number of times that specific character occurred previously. So in this case, we only have two characters, A and B. A appears 4 times, B appears 2 times. So the first appearance of A, we call it A0. The first appearance of B, we call it B0. Then A1, A2, B1, and then A3. Okay? And that gives us what's called the T ranking. Okay? So now what we're going to do is rewrite the Brooks-Reel transform, including these ranks. So basically that string here, with all the rotations sorted, we're going to rewrite them with all the rankings. And one thing that we could notice here is that if we look just at 2 columns, the last column, let's call it L, and the first column, let's call it F, and for now, let's just look at the A's. And the indexed A's, they occur in the same order. So A3, A1, A2, A0, A3, A1, A2, A0. They are ordered both in the last and the first column. And the same goes for B's. B1, B0, B1, B0. And that's called the LF mapping. It's a very interesting property that this is maintained. And with that, what we could do is then we would like then to do a different ranking for a given character, which is basically sorting our first column as in ascending order. Okay? And this will basically then give that we're always starting with the terminal character. And then we have A0, A1, A2, A3, B0, B1. Okay? And this order will be slightly different for L, but still in an ascending ranking. And this is called the B ranking. Okay? And F now has a very, very simple structure. So it's basically ordered. And we'll basically start then with the terminal character, a block of A's in ascending ranks, a block of B's in ascending ranks. And now we can basically throw away everything in the middle. That's the main important step for Brooks-Reel's transform. We only need the first and the last column to represent the whole data. So that's why it's reversible. And we reverse it in the following manner. So this is our original text, ABA, with the following indexes and the terminal character. So just with F and L, we can reconstruct the T as follows. Let's start then with the first row of F, which has the terminal character. And if we start with F, we always go to L. Okay? So L will give us the prior character from F. So basically, if we go from here to here, it's going to say what comes just before the terminal and what comes just before the terminal, and that's just looking at the sorted columns is A0. So just before the terminal is A0. And what we do is from A0, we'll go back from the L column to the F column. So we jump to the region or to the column of F or the row of F that has A0, which would be this one. Okay? And then we ask the question, what's the prior of A0? Which will be looking at L, which is B0. And indeed it is. So we look for B0 in F, which is here. And we ask the question, what's the prior of B0, which is A2? And indeed it's A2. And we look for A2 on F. What's the prior of A2 is A1. And so on and so forth. So we basically, by repeating doing this LF left and first and last mapping, we can recreate the original text from left to right. And we can use this to index. Okay? And this is called the FM index. It's not a special name. It's just the first name, last name of the two people that actually propose it. So it's not a very interesting name. So we can actually search for a given substring using Burrows-Wheeler transform. So we'll look for a range of rows, starting with one of the prefixes, and then start with the shortest suffix and then match successfully longer suffixes using this LM mapping. And it will work like this. We will have, let's say, we're querying for the word ABA. We'll then start asking the questions from F, where are the A's? These are the A's, which is the last one. So we always go from right to left. And then, given that we have all the rows that start with A, we ask the question, what's the next one? And the next one is B. And we ask, from here, which of these four have B next, which is these two? What we need to do is find the rows where B0 and B1 are on F, which is doing another round of LF mapping, which is these two here. And the next one is A. And then out of these two, we ask the question, which of them have actually A next? And we have these two. So we actually have two occurrences of ABA on our Burrows-Wheeler transform. Okay? And this is very, very efficient. So it has a considerably smaller memory footprint than any of the trees and the array as well. So if you consider indexing a human genome, while a suffix tree will take 40, 50 gigs, a suffix array will take 12, an FM index will take 1.5. Okay, so it's a very efficient way to actually represent information, but of course it will depend on your problem and your data, what's the best and most appropriate data structure you need. Okay, so always keep in mind, sometimes this is more efficient than a hash table, sometimes you actually need a hash table. So you need to actually understand your problem and your data and their limitations. Okay, and that's all for today. Thank you very much. Thank you for coming and for not